Today's problem is going to be add two numbers. We have two non-empty linked lists, L1 and L2, and each node represents a non-negative integer. And these integers are within the range of 0 and 9. So these digits are stored in the reverse order of an integer. So for example, this 1, 2, 3 actually represents the number 3, 2, 1, where each one of this is a digit. So this 3 at the very end corresponds to the first number, 2 corresponds to the middle, and 1 corresponds to the backmost number. So in other words, the head of the list is the least significant element, and the tail of the list is the most significant element. Now, this is how the question originally portrays the problem, but I find it easier to understand if I flip it around. So instead of worrying about reversing or whatever, I just flip the direction of the arrows and I can write it how we normally would read these things. So right now, this is our input of L1 and L2, and we want to add this up. We're basically adding 3, 2, 1 and 6, 5, 4. So, and then this next phrase here is saying that these numbers don't have any leading zeros, right? So if you have 321 and I add like a bunch of zeros here, it doesn't affect our number, right? So we can assume that our input has no leading zeros. And then we have to return the sum of the two numbers as a linked list, right? So if we just forget about the linked list thing, if we have 3, 2, 1, and then we add it with 654, we get 579, right? 975. And our usual process is that we add the smallest element first, followed by the next least significant number, followed by the next number. So it's the same thing here, right? We add this up. We want to return something that looks like this, right? This is going to be the head of our result list, and we're going to be returning this. So this was a pretty easy example because there are no carryovers. But if I show you another example, let's say L1 is the number 9 and L2 is also the number 9. And if I add this up, I'm expecting to get 18, right? So when I add this and I get 18, the 1 needs to carry over to a new node here. And of course, if I have a number 1 here, the sum of 19 plus 9 should give me 28 instead. So the 1 carry on would be added onto this thing, and that would give us this number here, right? So we have to be very careful about not just the carryovers, but also dealing with like nuns in general, right? So let's think about what it means when we actually add something. So let's say we want to add 654 and 745. We have our L1 pointers and our L2 pointer like so. This would be our input. Well, first thing that we want to do is of course add the value in L1 and L2, right? That's going to give us an 8. And 8's pretty easy because we can just create a node out of 8 and point it to something that we haven't decided yet. And then we can increment L1 and L2 like so, right? But it's not so easy when you have to deal with carryovers. So we have to take that into consideration because when we add 5 and 5, we're going to get 10. And we can't just create a node out of 10 like this. When we get a 10, we have to do a bit of processing. So I'm going to call the number that we're going to display in this node the val, right? So the value is going to be the sum of these numbers. In this case, it's 5 and 5, plus any carryovers that we have from the previous iteration. And well, in this case, we have 0. And well, this is the sum, right? The value is going to be the sum modulo 10, right? So right now our sum is 10. 10 modulo 10, well, 10 divided by 10 has no remainders. So that's why our value is going to be 0. And then we also need to calculate the carryover. And the carryover is going to be the sum floor divided by 10. So in this case, it's 10 divided by 10. So our carryover is going to be 1 for the next iteration. So in the real code, we probably have some kind of while loop that goes on here. And for now, I'll just say that we're going to keep going so long as L1 or L2 is not none. But this is just a placeholder, and we need a carryover variable that's set to 0 initially. So okay, now our carryover is 1, and we move L1 and L2. So at this point, the sum is going to be 6 plus 7, which is 13, plus our carryover, which is 14. So the value is going to be 14 modulo 10, which is going to give us 4. And then the carryover is going to be 14 floor divided by 10, which is going to give us 1. So our carryover is going to be 1. Now we reach the next iteration where L1 and L2 are pointing to none. So what happens here? Well, we know we still have a carryover. And since it's none, we basically treat them as zeros, right? Effectively, we want the sum to be 0 plus the carryover 1. And that should give us a value of 1 modulo 10, which is 1, which we can append here. And carryover would be 1 floor divided by 10, which would be 0. And then we'd go into a next iteration. And ideally, we shouldn't be erroring. Next iteration where L1 and L2 are none now. And not only that, we also have no carryover. So I guess we can put our exit condition to be like this, right? So we want L1 to not be none, L2 to not be none, obviously, but should both of them be none, we still want to run the iteration if we have a carryover. Otherwise, we wouldn't be getting this one, and our answer would be wrong. And that's the general gist of the algorithm. We just managed to add 654 with 754 in a linked list format. So let's get to coding. So first thing we want to do is define our carryover variable, and then we're going to need our while loop. But first things first, let's extract value 1 and value 2. For a more concrete example, I'm gonna make a comment here. So our L1 would start here and our L2 would start here, right? Now remember the issue that we had when we had L1 at none and we had L2 at none, but we still had a carryover. In that case, extracting the value like this without considering that the node might be none is gonna give us an error. So we need a contingency plan. So val1 is only L1.val if L1 is not none. Otherwise, if it is none, then it should be a 0 because we treat the value of nones as zeros. And likewise, L2, we're only taking the L2 value if L2 is not none. Next, we can calculate the sum, which is going to be val1 plus val2 plus our carryover, which is 0 initially. Let me just put this here. And then, as discussed, we can calculate the value of the new node that we're creating, as well as the carryover for the next iteration. And once that's done, we want to create that node with the value that we just calculated and then append that into our result list. So we need a variable that keeps track of our result list, right? So this is going to be the result pointer. You could put a none here, but that would be quite inconvenient because if I were to try appending to it and then incrementing it, this call would result in an error. So we're going to use another really common pattern in the linked list questions, which is to create a dummy node that our result pointer can point to in the beginning. So now we don't have to worry. We can run this result pointer.next without worrying about null pointer exceptions. So okay, at this point in time, we've just created a node and then we filled out the value inside and then we've appended this node into our result pointer with this line and then we have moved our result pointer to this new node that we've created. So this new node is still pointing to none right now and obviously we have to repeat this for the next iteration. The next thing that we need to do is to increment L1 and L2. But we have to be very careful here. So remember in the situation here where L1 and L2 are none and we had a carryover, which in the end gave us a new node of number 1 here. If I were to try and increment L1 by saying L1.next like this, it's going to error. It's going to raise a null pointer exception and it's going to crash. So L1.next should only run if L1 is not none. If L1 is none, then this code should not execute and L1 should stay none. If L1, else none. And this is pretty much the same thing for L2. So basically this while loop is going to keep running and processing every single node so long as there is a node left to be processed, and including the case where there are no nodes left but we still have a carryover. And once all that's done, we should have finished constructing our result already. So we can just return dummy.next and this will be our answer. And there you go. As for the time complexity, it's very clearly linear. Each element of L1 and L2 is getting processed exactly once. So it's linear. And we are using extra space to store our final result, but that's kind of necessary for this kind of question, right? So if you don't count that, this algorithm is O of 1. If you choose to count that, then it's O of n. But I would say that it's O of 1. All right, that's about it. Thanks for watching. Okay, bye.